Now our boundary conditions for this case is no slip conditions. One of them is at the wall. So if you look at this right here, at R is equal to big R, you have this solid surface here that is not moving. It's the wall of the blood vessel, so your VZ is equal to 0. The other one is at RC, which is the solid interface with the catheter, and that is VZ is going to be equal to the velocity of the catheter because it's moving in this direction, and I think it's at 10 centimeters per second. So these are your two boundaries, right here at the wall and right at the catheter, because you're interested in figuring out what is happening to the flow at these points right here, and because of symmetry it's also going to be happening the same way down here below here. So these are your two boundaries, because this is the boundary of these are the two boundaries of your flow that you're looking at. So what we can do is we need to now solve for our velocity profile. Alright, so we're going to start off with our governing equation. And then we know that delta P over L is equal to dP dZ. We have a constant pressure drop. So we can plug that into the equation. And we go ahead and integrate, and we see R tau RZ is equal to this right hand side of this equation. Then we can divide by R, and here's our equation for tau. So this is our shear stress, but we have this unknown C1 over here. So to figure out what C1 is, we're going to have to use our boundary conditions. But our boundary conditions, you remember, are all in terms of velocities. It's not in terms of tau. So we've got to get our velocity term before we can solve for C1. So to do that, we can use our constitutive relationship for Newtonian fluids, plug this into the equation, and you get this equation. Now you can integrate again because you want to figure out what VZ is equal to. And you divide by mu, and you have this equation. So this is your velocity profile with these two unknowns, C1 and C2. Now we're at the point where we can use our two boundary conditions to solve for C1 and C2. So the first boundary condition that we're going to look at is at the wall of the blood vessel. Little r equals big R, VZ equals 0. We plug it in to the equation that I just showed you, and we're able to find out what C2 is in terms of C1. Now we can plug C2 into back into our velocity profile. Now VZ is now in terms of only one unknown, C1. So we now need to use our other boundary condition, which is at the catheter wall, and that is equal to the velocity of the catheter. I have it as capital V. So we plug in capital V and RC, and we do the algebra, and we find out that C1 is equal to all of this right here. So now we've figured out what C1 and C2 are, and we can plug those back into our velocity expression, and this is what you get. So this is our velocity profile right here, and we can do some more algebra and combine certain terms. We can pull this out and combine these terms and combine these, and this is your final velocity expression of the fluid that's moving around the catheter. And what you can see from this right here, this portion right here, is the velocity due to pressure driven flow in a cylinder. So if we didn't have any of this right here, you could see that this is what would happen if you did not have the catheter. This other term right here is because of the catheter. If you actually break this down into two parts, and if you just looked at this part right here, this is the velocity, the effect of velocity based on just the movement of the catheter. That's why we have big V in this term. And then if you broke it back down into the other half, this whole part right here is the correction factor due to the catheter being in the center of the vessel, and you have this void space now where there's no flow. So this expression is describing the velocity of the fluid around the catheter. The next part of the question asks for the shear stress. So when we were solving for our velocity profile, we found that our shear stress was equal to this equation with that unknown C1. So now that we know what C1 is, we can go back to this equation and plug C1 in. And so that's what I've done here. Went ahead and I plugged in C1, and I just rearranged it algebraically, and we have tau RZ is equal to all this. So this is our shear stress expression in terms of little r. So now we were looking for what was the shear stress at the wall, because we want to figure out if the endothelial cells are going to detach. We can plug in the numbers given in our problem, and we found that the shear stress at the wall was about 40 dynes per square centimeter, which is much less than 400, so the cells are not going to detach. The final question, part of that problem, is asking for you to sketch the velocity profile of the catheter, of the flow around the catheter, and this is what your sketch should look like. And the reason why, on the edges, you know that VZ is got to be equal to 0 at these 2 points because of no slip, and you know that the velocity at this point has got to be equal to the velocity of the catheter. Now what you don't really know is if the pressure from the pressure-driven flow, if the maximum is going to be right here, or is there going to, are you going to have, is it going to be some concave shape? So what you have to do is look at the maximum is going to be at dVz divided by dr is equal to 0. If you go back, this was a relationship we stated earlier in the equation. We could just set dVz dr equal to 0 at this point. Solve for the radius. We have C1 delta P over L. We find that it is at 0.89 centimeters. So there is a maximum between RC, which is right here, at I believe 0.15, and this is at 2 centimeters. So there is a maximum in here around 0.89 centimeters. So this proves that there is a maximum at in between the two, and that's why you're going to have a kind of a parabola shape, and it's not going to go all the way down to 0 on this side because of the velocity of the catheter. Alright, so that's problem number 1.